Welcome back. We continue with our discussion of the relaxation of the modeling rules. In the last lecture, we had introduced the concept of weak laws and strong laws. In today's lecture, we'll consider the application of the same principle when the relaxation cannot be applied to the whole domain but to segments of this. This is called segmented modeling. In many cases, we cannot ignore a governing law throughout the entire range of investigation. But we can break up the phenomena either spatially or temporally and use few laws in each of the regions. Boundary layers in a fluid flow, we have discussed this before, is regionally segmented. One region near the wall where different laws are applied, viscous forces is important, and a region away from the wall, which is called the outer flow, where the viscous forces can be neglected. The change in phenomena as the time passes. We've done one example of the spreading of an oil slick where the surface tension kicks in after many days. We have also done examples where the phenomenon displays different behavior in different directions or at different speeds. We'll do a systematic study of this now. Sequential modeling. Sequential time-wise. One phase following the another. In modeling automobile crashes, the crash phase can be clearly distinguished from the post-crash phase. During the crash phase, which usually lasts only for a fraction of a second, tire friction forces are negligibly small compared to the large inertial forces of the impacting cars. Hence, the crash phase is governed by inertial forces and by energy dissipation in partially elastic and imperfectly smooth bodies of the cars. The tire friction forces do not come into play until the beginning of the post-crash phase, which may last for several seconds. The energy dissipation due to impact needs no longer be modeled in this phase. So two phases are modeled using different sets of laws. Another example of sequential modeling is the settling of microscopic particles in very low Reynolds number flow. This also we had done earlier. Initially, for a few milliseconds, both the inertia of the fluid as well as that of the solid are required. The fluid is accelerating, the solid is accelerating. Then, if the Reynolds number is very low, the fluid may be considered quasi-static after the first phase and its inertia ignored. But this solid is still accelerated. Ultimately, the solid body is traveling at the terminal speed, and the inertia, both the solid as well as the fluid, can be ignored thereafter. We had analyzed this in quite some details. Regional modeling. where the segmentation is done on space. In modeling of slow-moving off-road vehicles, the forcing frequency is quite low. And all the sprung and unsprung masses are considered as rigid bodies. Consequently, those masses are subjected only to Newton's law of inertia and gravitation. This represents the amplification of a spring dashpot mass model that we discussed. For lower frequency ratios, F divided by Fn, the natural frequency, when this is low, this is mass controlled motion. We can neglect all springiness in the system. And we can model this as if only the inertial forces are important and the gravity forces. On the other hand, all springs have negligibly small mass, follow only Hooke's law of elasticity, and all shock absorbers also having negligible mass follow only the law of viscous friction. So the masses of springs and of dashpots are ignored. Hence, the whole vehicle can be partitioned into separate regions where different laws apply, so that the masses are considered to be without any elasticity. The springs and dashpot are considered to be without any mass. Under these circumstances, modeling is considerably relaxed. Another case of regional modeling is, of course, the turbulent flow of a fluid through a pipe or channel. The inertial effects are confined to the main stream, whereas the viscous effects are confined to the vicinity of the walls. This difference permits a number of relaxation, because the major effects of viscous friction are restricted to the vicinity of the wall, where a large velocity gradient exists. The laws of viscous friction need not be expressed in truly general representative terms that would apply to any conceivable situation. Instead, it can be specified in terms of the boundary layer in which viscous frictions takes place. We apply this principle to an unrelated topic, the introduction of hydraulic radius in flow through non-circular pipes or in open channels. In such flows, the inertial effects are confined to the main stream, whereas viscous effects are confined to the vicinity of the walls. Consider this elliptical tube. I drew an elliptical tube because it was easy to draw on a PowerPoint, but it could be a tube of any section. The region within this is divided into two regions. The dark gray represents the boundary layer near the wall, within which the viscous effects play an important role. The light gray region in the middle, away from the walls, is a region where viscous effects can be neglected and only inertial effects need to be considered. So how does that help us? The viscous forces on the wall are like tau, the viscous stress, times the area of the wall, which is written as the weighted parameters times the length of the perpendicular to the plane of the screen. So the area here is represented by Pw times L, the weighted parameters times the length. Tau, of course, is the shear stress. There's mu times the velocity gradient. And the velocity gradient is in a thin region of thickness delta. So tau is estimated by mu v by delta. So this is the viscous force. The inertial force, on the other hand, is in the main region over the whole area. So that rho times the volume of the pipe cross section, LA, times the acceleration, which is v square by L, where L is the characteristic dimension of the cross section of the pipe. And so this gives us a force of inertia as rho A v squared. From these we get a Reynolds number like pi number, rho v divided by mu times A divided by Pw times delta L. Now there is a leap of faith. Consider two pipes of the same length carrying the same fluid at the same average speed. Two pipes, same length, carrying the same fluid at the same average speed. It stands to reason that the boundary layer thickness in the two pipes would be the same and flow would be similar if A divided by Pw of the two pipes are same. If one pipe is circular, the value of its A divided by Pw is obtained as pi d square by 4 the area and the weighted parameter pi d for a circular pipe. So this gives you A divided by Pw is equal to d divided by 4, where d is the diameter of the pipe. Thus, the diameter of a circular pipe, the flow through which may be considered similar to the flow through a given non-circular pipe, should be 4A divided by Pw. This is termed as the hydraulic diameter dH of the pipe. Thus, we could use all the formulation of a circular pipe for a non-circular pipe if the diameter d in that formulation is replaced by the hydraulic diameter dH, which is 4A by weighted parameter. Again, thus the pressure drop in a non-circular pipe can be predicted quite well by calculating the pressure drop in a circular pipe of diameter equal to 4A by P. 4 different pipes, a circular pipe, a rectangular pipe, an annular pipe, where the flow is between two diameters di and do, and a half-filled pipe. I calculate the hydraulic diameters of these 4 pipes. These are the hydraulic diameters. Using these hydraulic diameters for diameter in the Moody's chart, we can find out the head losses. The same principle can be applied to open channels. For open channels, the pressure does not change, and the change in non-gravitational pressure P is equal to P plus rho Gz is related to the change in elevation. So if this was a rectangular open channel, then the wetted parameter of this is 1 meter plus 3 meters plus 1 meter, 5 meters. And the area of the flow is 3 into 1, 3 meters squared. So we can calculate the hydraulic diameter as 4A by wetted parameters and treat this as a closed pipe of that diameter. The results that we get are very close to the result we get from much better analysis. Let's do one more examples of this segmented modeling. Testing of ship models. We are interested in finding out the drag on the ship. The drag on the ship as it moves in open ocean consists of two parts. One, the viscous friction termed as a skin friction on the surface of the ship in contact with water. The other resistance is related to the energy that is dissipated in the waves that move away from the ship. So the drag of the ship has two components, the skin friction drag and the wave drag. The wave resistance and the skin friction modeling would require the Reynolds number and Froude number match. Reynolds number invariance gives Kv equal to K nu divided by Kl, K nu for kinematic viscosity, and the Froude number invariance gives Kv as Kl raised to power 1/2. If the same fluid is used in the model as in the prototype, then the modeling without drastic relaxation becomes impossible unless we use Kl is equal to 1, which is hardly any modeling. But if different fluids are used, then K nu is like Kl raised to power 3/2, makes it possible to choose an appropriate Kl. If I can choose a fluid with the kinematic viscosity, which is much lower than kinematic viscosity of water. But even a small length scale of 1/100, this Kl of 100, would require a Kv of 1000. That means the kinematic viscosity of the fluid used in model study should be 1000th of the kinematic viscosity of water. Fluids of that low viscosity are not available. So this avenue is not open to us. Because of these conflicting scaling requirements, the hull friction, which is the skin friction, and the wave resistance cannot be modeled simultaneously. However, with friction effects confined predominantly to the hull's boundary layer and the gravity and inertia effects restricted to the waves around the ship, it is argued that the two resistances can be determined separately. The total drag, which depends upon Reynolds number and Froude number, is broken up into two parts. One, the skin friction drag, which depends upon Reynolds number, and the wave drag, which depends upon the Froude number. Now, skin friction drag is a well-studied topic and can be estimated from the skin friction on a flat plate. The sides and the bottom of a ship can be modeled as flat plates, and skin friction on them could be obtained analytically using the correlations for flat plates analytically. So how are the ship tested? We find the total drag on the model from a test run with fluid number similarity. So we use a KL which could be pretty large and run the test at a velocity given by the scale factor Kv is equal to under root KL, determine the total drag. Then calculate the skin friction drag on this model at the Reynolds number of the model. Determine at what Reynolds number was the test run and calculate using the flat plate formula the skin friction drag on the model. We subtract this skin friction drag from the total drag to obtain the wave drag on the model. The wave drag on the model must be scaled by using the fluid similarity. So predict the wave drag of the prototype from the model wave drag. The drag coefficients, the wave drag coefficient on the model must be equal to the wave drag coefficient on the prototype. And since we know the wave drag on the model, we can calculate the wave drag coefficient on the model. And this same drag coefficient would apply on the prototype. And using the 1/2 rho v squared times the area of the prototype, we can predict the prototype wave drag from the model drag. Now we calculate the skin friction drag on the prototype at prototype Reynolds number. I know the prototype Reynolds number, so I can use the flat plate formula to calculate this skin friction drag and then add this skin friction drag to the wave drag predicted in the earlier step to obtain the total drag on the prototype. This is the scheme of testing of ship model for drag that is employed almost exclusively. Directional modeling. When governing laws work in distinct directions instead of distinct regions, directional modeling can relieve stringent scaling requirements. We have done this earlier in a different context. For example, if the turbulent flow in rivers and estuaries were faithfully scaled in horizontal direction as well as in depth, river models would be so shallow that the turbulent flow would be suppressed. And in addition, unwanted surface tension would be exaggerated. With directional modeling, the depth of rivers and estuary models are very often disproportionately magnified. We use a smaller scale factor for the depth than for the length and width. Fully turbulent flows in a slope channel is governed by Newton's law of inertia and the law of gravitation. But the inertial forces act predominantly in a horizontal direction, while the gravitational forces act in a vertical direction. And since these two forces act in different dimensions, we can use different scale factors in the two directions. This picture is from a section of a Mississippi River Basin model, which is spread over 200 acres. This was constructed in 1943 and decommissioned in 1967 after giving wonderful results. After that, the computational models kicked in, and it was no longer to maintain this very, very expensive model. This model for length uses a scale of 1:2000. So 2000 kilometers are represented by 1 kilometer. This is a huge model spread over 200 acres. In a river model, inertial and gravitational forces are important. And this again results in the fluid number similarity. Inertial force scale factor and the gravity force scale factors give you Kv is like under root Kl using the same fluid. So K rho is 1 and Kg is 1. And for a 1:2000 scale model, this gives you Kv of 44.7. The surface tension forces, scale factor for surface tension forces is like K sigma times Kl, which gives you the ratio of the surface tension force to the inertial force as sigma divided by rho L V square. And for the prototype, this gives you a value of 2.6 into 10⁻⁻⁶, very low. So the surface tension could be neglected in the prototype. For model flow, if we follow same dimensions for the depth, 1:2000, then this gives you the skin friction force over inertial force of the order of 10. Definitely surface tension forces cannot be neglected in the model. So obviously, a model run on the basis of fluid similarity would fail, because though the surface tension force in the prototype is negligible, it is non-negligible in model flow. So the model flow is not really modeling the prototype flow correctly. So what do? Look at a sloping riverbed. If we consider a slice of the fluid on this, the weight forces are rho Z L square G. L is the horizontal dimension, Z is a vertical dimension. The slope is Z divided by L. And the component of the gravity force in the flow direction then is rho G Z L square times Z by L, the slope. Inertial forces of the flow are rho ZL square. ZL square is the volume now. L by T square is the acceleration. So the ratio of the gravity forces, this gravity force and this inertia force, now leads to a fluid number which is Gz by V square, the same as before except L has been replaced by Z. So this permits us to use a different scale in the Z direction than the scale in the length direction. Then the scale factor for the volume flow rate is Kv, Kl, Kz. And since Kv is like Kz square root, so that Kq is Kl, Kz raised to power 3 by 2. The developed pi number for channel flow allows for a large difference between the horizontal and vertical scale factors. The vertical scale factor is reduced. The Mississippi Valley model uses KL is equal to 100 in the vertical direction, so that the Weber number becomes of order of 0.5 less than 1. And so the surface tension effects, even in the model flow, are almost negligible. This example illustrates a very important point in relaxation. Before disregarding a law, we must satisfy ourselves of its insignificance not only in the prototype but to the model as well. Too often, a law of little importance to the prototype assumes great importance when applied to the model. Therefore, in very small models like harbors and estuaries, surface tension is no longer insignificant unless we increase the depths. Let's do one more detailed example. Flow through porous media is governed by viscous friction between fluids and the solid grains of the porous media, the inertial force of the liquid, and the weight of the fluid. Hence, the correct modeling requires matching of the Reynolds and Froude number. This leads to the result that KL must be 1 if the same fluid is used. Because from Reynolds number, we get KL is equal to K nu divided by KV. And from Froude number, we get KL is equal to KV square divided by KG. If K nu and Kg are same, these two equations can match only if KL and KV both are 1. If we use a different fluid, we need a fluid with scale factor of kinematic viscosity as KL is to the power 3/2. A requirement impossible to meet for large scale factors. Hence, the problem is solved by employing two different length scale factors. Realizing that there are two lengths, a length L which characterizes the porous media, the sand bed, and a length Z which characterizes the gravity force which is moving the water through the porous bed. In the test, sand of uniform grain size was held in the bottom of a glass tube by thin cloth with negligible flow resistance. When the tube was filled with water, gravity made the water flow downwards through the sand. Tests were performed with sands of 3 different grain sizes, with the depth of the sand layer made proportional to the grain size to maintain geometric similarity. Because the effects of gravitation depends on the water column vertical height Z, while the inertial and viscous effects are confined to the layer of sand with the characteristic dimension L, we can describe seepage by two representative lengths Z and L. Note that L represents the dimension of the sand layer as well as the grain and void sizes. So, when we are using a scaled length L, this sand size has to be reduced. With these relaxation, we can write the representative versions of the 3 governing laws as follows. Inertia of the fluid flow in the sand layer, characteristic length is L here, mass times acceleration, mass is rho AL, L being the characteristic length, and the acceleration is v square by L. So this gives you pi number for inertial forces F divided by rho A V squared. Viscous forces in the same layer, characteristic length L. So force is mu V divided by L times the area. So that the pi number is FL divided by mu AV. And the gravitational forces. Now this is because of the column of water of height Z. So this is rho ZG times the area A, and this gives you F divided by rho ZAG as the pi number. The two modeling rules for the same fluid, water, so that rho and mu and g are scaled by a factor 1. From the first equation, we get LV is invariant. On the second equation, we get Z divided by V square is invariant. This is the results from the test held on such a model as reported by Ebori. This region, log of LV by nu is inversely proportional to GZ by V square. If we compare, if we look at this carefully, we see that this inverse relation means that in this region, the inertia force is an important, and only the viscous force need to be considered. But in this region, GZ by V square is independent of LV by nu. So this leads to the conclusion that this region can be modeled as non-viscous. So larger value GZ by V square is the inertia forces that count, not the viscous forces. One more example. One of the factors that unfavorably influence the transport rate of fluids in channel with sediment beds is the formation of ripples or miniature dunes on the bed. This GIF shows the motion of the granules on the bed of a beach with waves. The small irregularities in the bed give rise to vortices whose increased velocity causes particles of the bed to move out of the range of the vortex and to settle down at some distance, thus serving to generate a new vortex, and so on. We need to determine the dominant mechanism here. What is that causes this sediment waves? We could think of 5 different forces. Inertia of the solid particles, which would be like rho s L square V square. Inertia of the fluid, which will be like rho f, the density of the fluid, times L square V square. The gravity of the solid particles, the gravity force, the weight of the solid particles, which will be rho s G times L cubed. And the viscous forces, which would be like mu VL. Mu is of the fluid, so mu is replaced here by rho f, the density of the fluid, times kinematic viscosity. Inertia of the fluid and viscous forces gives you a Reynolds number. VL by nu should be invariant, and the inertia of the fluid and the gravity force will give you the Froude number, V square by GL. And from this, we get L cube by nu square as invariant, the pi number that control this flow. If we use water as a model material and 49.5% glycerol solution as prototype, we get K nu is equal to 5.2 and then KL is like 3, which is not large enough. And if we do that, K rho is equal to 1.27 for the two fluids must apply to solid particles as well. The density ratios for the glycerol and water is 1.27. And so this must apply to the solid particle as well. Same density scale factor should be used. Cold particles with a density of 1.26 kilogram per meter cube and the eraldite epoxy resins with a density of 0.999 kilogram per meter could be used as the prototype and model sentiments. So it is possible to construct a model with glycerol and coal particles. But since length scale factors was not satisfactorily large, it was decided to use water itself as a model fluid and add a relaxation. With the same fluid, Reynolds and Froude numbers would result in conflicting model requirements. This could be avoided, however, if the inertial force of the sediments were much smaller than the rest of the forces and therefore could be neglected. Inertia of the fluid is rho f L square V square. A further simplification results when, without loss of generality, we restrict the gravity to the wet weight of particle. So the weight force is now considered rho s minus rho f times GL cubed. These two results in rho f V squared by rho s minus rho f times GL, a modified Froude number, which is known as a densimetric Froude number, as a pi number. And the inertial and viscous forces gives the Reynolds number as the other pi number. Rho f VL by mu for the same fluids gives Kv is equal to 1 over Kl, and the densimetric Froude number for the same fluid gives you Kv is equal to under root K of the density difference times Kl. And from this, by eliminating Kv, we get Kl as the cube root of the scale factor for the density difference, rho s minus rho f. The model tests were performed in a tilting frame 18 meter long and 65 meter wide. The model sediment was sand with a density of 2.65 kilogram per meter cube. The prototype sediment polystyrene with a density of 1.035 kilogram per meter cube. The fluid water with a density of 1000 kilogram per meter cube. With these data, Kl is equal to 3.6. The average grain diameter of the sand was 0.375. Therefore, the grain diameter of the polystyrene sediment was made 1.35 millimeter using the same scale factor of 3.6. So this was the testing arrangement. This flume was inclined at an angle alpha. Alpha adjusted such that it gave you the required flow rate. The same flume was used for model as well as the prototype test, since it was assumed that the formation of sediment waves is a two-dimensional process. Kv is like 1 over Kl. The necessary speeds were achieved by tilting the flume by a very small angle. Model and prototype tilting angles were computed from the representative gravity components in the flow direction, that is rho f GL cube times alpha obtained earlier, where alpha is the tilt angle. Hence, a new pi number was introduced with inertial forces GL alpha V square. For two-dimensional flow, Q is like V B H, where B is the flume width and H is the flow height. For constant flume width, KQ dot is like KVKL is equal to 1. Also, KH is equal to KL is equal to 3.6. And if you plot this, we get this curve. Onset of fluid particle motion is called V critical. And this plots V divided by V critical versus lambda by D, the wavelength divided by the diameter of the grains. And we obtain this curve where all points collapse onto one curve, suggesting that the formulation is correct. Thank you very much.